Hello and welcome back to AP or Honors Topics in Physics. Um, so let's see, let me get on the right screen. So what we're covering in this first unit is momentum, and I'm sure you've heard of getting momentum or momentum before. What is momentum and how do you get it? I have a rather cheesy joke of a guy going to the momentum store and requesting some momentum. And then out comes this cowboy boot with kicks him, which gives him some momentum, which did technically give him some momentum. Momentum is basically how hard it is to stop something. So something that has a lot of momentum would be very, very difficult to bring to a stop. So what would make something really hard to stop? Okay, probably one, if it had a lot of mass, and two, if it was moving very quickly. Okay, those would be the two things that would make something very difficult to stop. So an object with a lot of mass moving very quickly has a lot of momentum. Okay, so when we write our equation for momentum, it should have these two things in it. It should have mass and speed. And we'll get to that in a minute. So if you've ever played Rover, Red Rover, Send One On Over, you have a group of people that hold hands and they form a chain. And then the opposing team sends a person and they go running and they try to break through the chain. And if they break through the chain, then I don't know what happens. They get a point or something like that. So in terms of momentum, why do you run instead of walk up to break the chain? Well, A, you want to have a lot of momentum because you want to be very difficult to bring to a stop. You want to just keep on going, so you want to have a lot of momentum. But why do you run? Well, when you run, you have a lot of velocity, which would give you more momentum. And if you were picking teammates, okay, you've got person A and you've got person B, who would you tend to want to have on your team? Who's going to be harder to bring to a stop? It's going to be person A because they have more mass than teeny person B here. So you would tend to want them on your team. But to be nice, we got to include person B because we don't want to hurt anybody's feelings. Okay, so more mass for given speed is going to have more momentum. So this is our equation for momentum. The symbol for it is a P. Okay, instead of using an M, because we've already got an M for mass, we can't use M, so we use P, which comes from an early understanding of momentum when it was called progress. So P for progress, but it really means momentum, and that is equal to mass times velocity. Mass will be in kilograms as always, and velocity will be in meters per second as always. And when we multiply these two together, we're going to get a kilogram meter per second, and that's going to be what's on that's going to be the units of momentum. It can also be a Newton second, but you know, it doesn't really matter. So are any of these vectors? Is mass a vector? I don't think mass is a vector. Is velocity a vector? I think velocity is a vector. Okay, so that means that momentum itself is going to be a vector. Okay, what would be the direction of your momentum vector? It's just going to be the direction of your velocity. It's which way you're going is going to be the direction of your momentum vector. So, so what would happen to the momentum of a cannonball if its speed doubled? Okay, well, if I double the v, okay, I'm going to double the momentum. I'm going to double the p too, so it's going to be twice as much. Okay, what would happen to the momentum of the cannonball if it was cut in half, and we just looked at one half of the cannonball? Okay, well, it's going to have half the mass, which is going to have half the momentum. Okay, what would happen to the momentum of a cannonball if I doubled its speed and doubled its mass? Okay, when you double both, you're going to get quadruple. Okay, so it will quadruple. Would it be possible for a big old heavy bus and a teeny weeny little bug to have the same momentum? What do you think? Well, yes. There's two different ways that they can have the same momentum. One is if they're both at rest, then they both have zero momentum and they'd be the same. Or the bus could be moving very, very slowly with its large mass, and the bug could be moving very, very quickly with its small mass and have a higher velocity with a smaller mass, and they could have the same momentum that way. Let's say we had a scenario if we had a boulder which was chasing the boy. The boulder is obviously heavier than the boy, much more mass. and if I said they have the same momentum, okay, will the boulder crush the boy if they have the same momentum? Okay. Well, if they have the same momentum, since the boy has less mass, he's got to have a larger velocity, okay, which means he's running faster than the boulder, which means he's going to outrun the boulder, which is good. Yay! Okay. Bring, bring. So what is the momentum of a 10 kilogram object moving at 20 meters per second? So I'm given my mass and my velocity. So momentum is mass times velocity, so it's 10 times 20, which should be 200 kilogram meters per second. Okay. How fast would a 40 kilogram object be moving if it has the same momentum? Well, if I've got a 40 kilogram object that has 200 units of momentum, what number over here is going to make 200 with 40? That's going to be 5. Okay, the other way to look at it is this has 4 times the mass, which means it's got to be moving at 1/5 velocity, or 1/4 the velocity, in order to have the same momentum. Okay, what is the momentum of a 1,200 kilogram elephant if it is at rest? Well, if it's at rest, the velocity is 0, and anything times 0 is 0, so the momentum is 0. So momentum is a vector. What would the direction of the vector mean? As we already said before, it's the direction of the momentum vector is just the direction that it's moving. There's nothing complicated about that. To the right, to the up, north, south, west, anything, whatever. Okay. So if the mass remains constant, what is a change in momentum vector from top to bottom? What would that mean? Well, my momentum vector got shorter, which means I must have less momentum. When if the mass remained constant, in order for me to have less momentum, that must mean I got moving slower. Okay. What happened to my momentum vector now? Well, I just switched directions. It looks like I'm going about the same speed, just to the left instead of to the right. Okay. And so up here we have positive momentums, and down here we would have negative momentum vectors. Okay. So what is the velocity of a 750 kilogram rhinoceros if its momentum is negative 2,800 kilogram meters per second? So plugging this in, so our P is negative 200 or 2,800. Okay, our M is 750, and we're looking for V. Okay, so solving for V, we get negative 3.73 meters per second. And what does a negative mean? It means it's traveling backwards or to the left, or it's one of those things. Okay. How do you change the momentum of an object, or of like a car that's got a constant mass? How do you change the momentum of your car? Step on gas. Okay. You accelerate. You have a change in velocity. You accelerate. And how do you accelerate an object? You do that with a push or pull or a force. So when you apply a force, you change the momentum of an object. But there's two things about that force that determine exactly how much the momentum is going to change. Okay. One is how hard you push, or how far you push the gas pedal, which is going to determine how much force is accelerating the car. The more you push the gas pedal, the bigger the force that's accelerating, and the more you're going to speed up, and the more your momentum is going to change. And the other is simply how long you push the gas pedal. The longer you have it depressed, okay, the more your momentum is going to be changing. Okay, so there's magnitude of the force and the duration of the force. So a force applied over time is called an impulse. And this is an important concept. Impulse equals force times time. Okay? So F is the force, the magnitude and direction of the force, and T is how long that force was applied. You don't really need that delta there. It really can just be force times time. Okay. And what I'm going to try to drill into you is that impulse equals the change in momentum. You apply an impulse of 5 units, you get a change in momentum of 5 units. Okay, so okay, I can derive the equation for impulse equals change in momentum pretty quickly. We start from Newton's second law, F equals m times a. And acceleration, if you recall, is equal to the change in velocity over time. Okay, so if I substitute that in for acceleration, okay, I get force equals mass times change in velocity over time. And if I multiply through by delta t, okay, what I get is impulse, which is force times time, equals change in momentum, which is mass times the change in velocity. M times delta v is delta p. Okay, so the applied force and how long that force is applied. Okay, I can, if you don't believe me that this is change in momentum, I can show you real quick. So delta v is really v2 minus v1. Okay, so if I substitute that in, okay, then if I go ahead and multiply through by my m, okay, I get mv2 minus mv1, okay, where mv2, mass times velocity 2, is going to be my final momentum, mass times velocity 1 is going to be my initial momentum, and p2 minus p1 is delta p. So impulse equals change in momentum. Drill that into your mind, okay, especially by the lots of exclamation marks. Impulse equals change in momentum. So if you know the change in momentum in a problem, you automatically know the impulse. Because I'll do that to you. I'll have you calculate the change in momentum, and then I'll ask you what the impulse is. And some people will work a whole nother problem instead of just saying it's the same thing. Okay. So all forces are applied over some finite period of time. That all forces really can generate an impulse. You can see things that even happen very quickly still take time for that to happen. So here we've got a tennis ball that's reflecting off of a racket, and it does so very quickly, but you can see it's stretching the spring of the strings backwards, and that takes time. When you drive a golf ball, it looks like that ball leaves the club instantly, but it takes time. That golf ball will deform and flatten on one end and rebound off. So all forces create impulse. So when you're trying to change the momentum of a ball, let's say you're at softball or baseball practice, and a ball is coming towards you, and you want to change its momentum by as much as you can. You want to get it going the opposite way as fast as possible. Okay, there's two things that determine the change in momentum of that ball. Again, it's force and time. The magnitude of the force, which is how hard you swing. You don't swing the bat lightly. You swing it as hard as you can. And how long that you apply that force to the ball, which is why your coach, I'm sure you've heard this sometime in batting, follow through. Okay, don't just swing and stop. Okay, by following through, you're maintaining contact with that ball for a longer period of time, and you're going to get a greater change in momentum of the ball. So, and don't forget, impulse equals change in momentum. Okay. So let's say that you're going to come to a stop. There's two ways that you can come to a stop. You can crash into a wall, okay, which means you come to a stop very quickly with a short period of time with a large force, okay, or you can apply your brakes and come to a stop very slowly over a long period of time with a small force. Both require the same change in momentum, the same delta P. If you go from 60 miles an hour down to 0 miles per hour, no matter how you do it, you have the same change in momentum. Okay, but again, it just depends on how the impulse is applied. So coming to a stop quickly requires a large force, big force, small time. Okay, applying your brakes means there's a small force and a much greater time. So if you can extend the time over which a force is applied, you can reduce the magnitude of the force, or you can reduce the strength of the force. Okay. So for example, if you drop a glass, so these are supposed to be glasses, and this is supposed to be on some cushiony surface, and this is on the concrete, the little rocks in it. It's a lot more likely to break when it hits the concrete. Okay, why? Well, there's a couple different reasons. Okay, one has to do with what we're talking about. When the glass hits the cushy carpety, that doesn't really look like carpet, but pretend it's carpet, it sinks into the carpet, and in doing so, that force is applied for a greater amount of time, as it's being slowed down the whole time it's sinking in. Whereas when the glass hits the concrete, it doesn't sink into the concrete, it bounces off, so it comes to a stop very, very quickly. So we've got a large force on the glass with a small time, and that large force tends to break the glass. The other reason is that the cushiony surface will cup the cup and distribute that force over a greater amount of surface area as well, so it reduces the pressure that's being applied. But that's not really what we're talking about, but that definitely is a factor. Whereas this applies that force over a concentrated area. Okay. So let's say you're on your roof and you want to reach the ground. You want to jump off to the ground, and so you're going to gain some momentum just before you hit the ground. You're going to come to a stop. So you're going to have an impulse. You're going to change your momentum when you hit the ground. And we all know the best way to jump off of a roof is to land with your legs straight and locked. Okay, right? Just stick the landing. Okay. No, that's probably not you'll come to a stop very quickly, but that will require a large force, and that could break bones or do whatever, depending on how high you're jumping from, strain ligaments and whatnot. What you want to do is you want to bend the knees when you touch, and then roll. So extend the time over which that force is slowing you down. By extending the time, you reduce the force. If you've ever heard the term rolling with the punches, basically there's two different ways you can get punched. You can stay locked and have this person's fist punch into your face, and you just remain right there. Okay, or you can kind of roll back with the punch, and you can kind of extend the time over which that fist is being slowed down by your face. And by extending the time of contact of slowing, you decrease the force. Bigger time, smaller force. Okay. Okay. So what is the momentum of El Nino rolling along at 2 meters per second? Okay. So what is the change in momentum if El Nino comes to a stop? Okay. What impulse would be required to do this? And what force would be required to stop El Nino in 10 seconds. So we're going to start with A. What is the change in momentum if El Nino comes to a stop? It was traveling at 2 meters per second, 6 kilogram mass. Okay, so my initial momentum is 6 kilograms times 2 meters per second. It gives me 12 kilogram meters per second units of mass or of momentum. It comes to a stop, so my final momentum is 0, 6 times 0. Okay, so that's that. What is my change in momentum? So don't forget it's P2 minus P1. That should be P2 minus P1. That kind of looks like a 2, but that's really a 1. So that's 0 minus 12, okay? And that gives me minus 12 kilogram meters per second. Now, if you did it the wrong way, you'd end up with a positive number, and that wouldn't be correct. Okay, so now I know the change in momentum. The next question B was, what's the impulse? Okay, well, impulse equals change in momentum. So it's just minus 12. I told you I'd do that to you. Okay, it's an easy answer. C, okay, if the force is applied for 10 seconds, how much force would be required to bring it to a stop? What we're doing is we're saying impulse equals change in momentum. Ft equals delta P. So, and I'd make sure you've got that equation written down somewhere, helpful to look at. So force is what we're looking for. T is time, okay, and delta P we just calculated was minus 12. So solving, we get that the force is equal to minus 1.2 newtons. Okay. So what is the significance of the negative? Well, it means that the force was applied in the negative direction. Okay. So if El Nino was rolling to the right in the positive direction, then we stopped it with a force to the left. That's all that means. Okay. A 25 Newton force accelerates a 1,200 kilogram car from rest to 20 meters per second. What's the change in momentum? What's the impulse? And how much time did it take? How long did it take? So again, we want to find the change in momentum. So it was originally at rest, so my P1 is 0. Okay. My P2 is 1,200 kilograms times 20 meters per second, so 24,000 kilogram meters per second. Find my delta P, that's P2 minus P1, so that's equal to just 24,000 kilogram meters per second. And that's positive this time because my final momentum is positive, is bigger. Okay. The next question is, what's the impulse? Okay, 24,000. Okay, same as change in momentum. And then finally, if a 25 Newton force is applied, how much time will it take to do this? Okay, so Ft equals delta P. Remember that equation. So we're given that the force is 25, the time is T, that's what we're looking for, and the delta P we know from before is 24,000. So dividing both sides by 25 gives me 960 seconds. Okay, which has a greater momentum? A ball that hits and sticks, okay, hits and stops, or one that bounces back? One that just hits and sticks, or one that bounces back? Okay, well, I'm going to go through this fairly quickly. So if the ball hits and sticks, okay, its change in momentum, well, its final momentum is 0, okay, because it hits and sticks, its final momentum is 0. And we subtract from that the initial momentum, which was its 1 kilogram times 2 meters per second. Now we're subtracting off a positive 1 times 2, okay, and we get minus 2. So if it hits and sticks, my change in momentum is negative 2, okay. If it hits and bounces back, okay, well, this is P2. It'd be so much easier if I could write on the board. I don't know why I didn't do this on paper, but you get the hint from, or get the gist of it from this anyway. So this is P2, my 1 kilogram times minus 2. It's moving to the left in the final picture, which is why it's that 2 is negative right here. So that's P2 minus P1. Okay, and when I calculate this, I get minus 4. So it actually has twice the change in momentum when it bounces back at the same velocity as it entered. So bouncing has a bigger impulse and a bigger change in momentum. So which would hurt more? Getting hit by a flower pot that hits and just stops on your head, or getting hit by a flower pot that hits and bounces back? Okay. Well, getting hit by the flower pot that bounces back is going to have a bigger change in momentum and a bigger impulse, and it's going to deliver a bigger impulse to your head, and it's going to hurt more. There was what's called the Pelton wheel. This is a water wheel, and instead of just having the water hit the flat blades of the water wheel, this guy found that if you caused the water to curve backwards and bounce, in a sense, okay, that you'd be able to get a lot more work from the same amount of water. So this was his water wheel called the Pelton wheel. Almost done. Yeah, there we go. Last problem. Let's say we've got a 2 kilogram ball moving to the right at 4 meters per second and then bounces to the left at 4 meters per second. What's the change in momentum? Okay, so my initial is 4 meters per second to the right. My final is 4 meters per second to the left. Okay, and so my P1 is 2 kilograms times 4 meters per second is 8. Okay, my P2 is 2 kilograms times negative 4. Okay, so that's a negative 4 because it's moving to the left at 4 meters per second. So I get negative 8. So when I find the delta P, that's P2 minus P1. So that's P2, which is minus 8, minus P1, which is 8, and I get negative 16 kilogram meters per second. Okay, so work on momentum and impulse worksheet 5-1. Don't forget to show your work, and thanks for sticking with me.